Okay, so the last topic in this unit is general rational functions. Now we kind of did this when we looked at the simple rationals in general form, this standard quotient form here. But now we're going to generalize that so that it's not just a linear equation over a linear equation. So now we're dividing actual polynomials. That means instead of just sum y equals mx plus b, I now have a quadratic maybe, ax squared plus bx plus c, over some other polynomial, maybe a cubic, dx cubed plus ex squared plus fx plus g, or something like this. So now we're dividing more than just linears. So in simple rationals, we had the hyperbolas, and we were able to find the intercepts and the asymptotes here, and both were linear expressions. So y equals mx plus b, y equals mx plus b. So if you recall, the denominator equal to 0 give us the vertical asymptotes. The numerator equal to 0 give us the x-intercepts. The ratio of the leading coefficients give us the horizontal asymptote. And the ratio of the constants gives us the y-intercepts. So we're still going to be looking at that, but now we're going to have additional points. So we might have multiple vertical asymptotes or multiple x-intercepts, depending on what the polynomial is. Okay, so here, let's just look at a more generalized form. I know there's a lot of letters going on here, but once we put numbers to them, it's not that confusing. So here, most rational functions are more complex than just the quotient of two linears. So here, this is a general form generalizing that. Exponent can be anything. These a's are numbers. The b's are numbers. So an and bn are just coefficients. And specifically, they're the first ones, so they're the leading coefficients. But all of these a's are just numbers and coefficients. The only variable in this entire thing is the x. Everything else is a number. So like right here, if we make a number for an, we can do 5x to the 5th, and then we just go down 1 plus 4x to the 4 plus 3x cubed plus 2x plus, or 2x squared plus 1x plus, I don't know, 6 is the constant. So that's all this means, is that you start with the highest one first and then you decrease, and then same thing for the denominator. B, or N and D here are your highest degrees. They're your biggest exponents. We call the highest degree, we call the biggest exponent just the highest degree. Same thing. Alright, the last two numbers here are your constants. So the ones without the x are still your constants, so we're still going to need those. And if it's not, you always want to write them in decreasing order. So you write your highest exponent first, and then you go down all the way to your constants. You might skip some in here, you might not have every single term, but you always start with your highest degree, and then you just decrease as you go to the right. Right, so most of the time they're given in this form, in standard form. But now these are what these graphs are kind of going to look like, but not all the time. There's no rule as to what these all look like. They all look a little different. Okay, so we have a lot of the same critical values as we did before, but now we add a fifth one. So x-intercepts are still where the graph crosses the x, which in this case would be this point and this point. So x-intercept, x-intercept. And these are always given as coordinates. So x1, 0, x2, 0. You might have multiple ones. You might have 2 or 3 x-intercepts. So where the graph crosses the x-axis. Y-intercept, where the graph crosses the y-axis. And you're only going to ever have one of these. You can't have multiple, because then you won't have a function. So or y-intercept. And this one's always given as a coordinate, 0, and then whatever your y is, wherever it crosses the y. Alright, so in this case, let's go ahead and write it over here. The x-intercept, it's about 2 point, I don't know, maybe 2.5 or something. I think the actual one is 2/3. But here we would just approximate it. If you said 2.25, that would be fine. And then over here, approximating the x-intercepts, or we can do the exact ones here. We have -1, 2, 3, 0, and then +3, 0. We're going to need those numbers on the next page. Actually, no, I think it is 2.25 up there. So up here. So 1/4, or you can write it's 2.25. Alright, the vertical asymptotes are these dashed lines that the graph does not cross. So the vertical asymptote here and a vertical asymptote here, which are the x equals numbers. So there are the dashed lines, and we say those are breaks in the graph. Where the graph jumps from one to the other. So over here, there's one piece over here. Then it has to jump way over here across the vertical asymptote to this side. And then it jumps again down here. So these are always given as x equals a number. So wherever these vertical dashed lines are. There might be multiple ones. So in this case, there's plus and minus 2. If you have 2 vertical, you could have 3, you could have 4. Like I said, there's no general rule for these. Alright, and then we have the horizontal asymptote, which could not exist. We could have something else called a slant asymptote. But this is basically what happens in the end. So this is your end behavior. So here the dashed line, the horizontal one is at y equals 1, so it's always y equals a number. But it's not going to be always a number. It can be slanted. So that horizontal asymptote can actually be a slant asymptote eventually. And really we care about what happens towards the ends. What's happening at the ends, they're getting closer to 1 here, and they're getting closer to 1 there. So what is it getting closer to as you go out left and to the right? Alright, and then this is the new one. So a removable discontinuity is basically just a hole in the graph. So notice here you have an open circle. So that's a hole in the graph. So here I say hole. I don't say removable discontinuity. That's too long to say. So here's one hole, and then over here is another one. Open circle in the graph is another hole. And you always give these as coordinates. So like this hole looks like it's at 1, 2, 3, 4, 5, -5, something, almost close to 1. Maybe like 0.75. We'll figure it out exactly on the next page, but right now we're just estimating using the graph. And then this one looks like it's at 2.75 again, maybe. Again, we'll figure this out exactly on the next page. 75. Okay, but these are the critical values we're looking for now. They might not always have 1. Sometimes it's none. You just say none. But this is an example of what the graph might look like. They're all going to look a little different. Okay, none of these looks exactly the same. Alright, so reviewing our ABCD information. Now we're extending it. So let me see if I can get all of this on one page. Yikes, this is going to be hard. Okay. So here, This is actually the equation, both the equations for this graph over here. But we have two forms. We have standard form and factored form. Standard form, there's no parentheses. You multiply everything out so that it's in a standard polynomial up here and a standard polynomial down there. And then factored form, you have to factor it so that it's all in factored form. It's all being factored, all in parentheses. So all parentheses, which means everything is being multiplied. Okay, so I'm going to review the ones that we did last time, because those are pretty much the same thing here. So from ABCD form, I'm going to kind of write it to the side. We have AX plus B over CX plus D. The y-intercept in this form was the ratio of the constants. The y-intercept here is still the ratio of the constants. So y-intercept occurs when x is 0. So if x is 0, this is 0, this is 0, everything else is 0 except the last two numbers. So to find the y-intercept, we cover up the x's and use the ratio of the constants. Okay, so that one's the same. That one we treat exactly the same way. For this one, for the horizontal asymptote, in this form, this was the a over c. Now, it is a over c. It is the numbers in the front, which in this case would be 1 over 1, if the exponents are equal. So to determine the horizontal asymptote, first look at the degrees of the numerator and the denominator. If they are equal, so I'm calling the degree of the numerator n and the degree of the denominator d. If they are equal, so both right here they're both 4s, right here they're both 1s. If they're equal, then you can look at the two numbers in front, which is a over c. And that's the ratio of the leading coefficients. However, if it's not equal, if the numerator happens to be less than the denominator, so let's say the numerator is like a squared and the denominator is like maybe a cube. So if the highest exponent here is less than that, the asymptote is always 0, regardless of what the numbers are in front are. And then the other direction, if the numerator is greater than the denominator, so like x to the 4th and then x squared, then this thing has then the graph does not have a horizontal asymptote. It might have a slant, and we'll get to this in just a second. So it might have a slant if the numerator is exactly 1 more than the denominator. So if the numerator is like cubed and the denominator is like squared, if it's exactly 1 more, then it has a slant. But again, we'll get to that later on in these notes. Okay, so those are almost the same. Constants are exactly the same. This one is almost the same. You gotta pay attention to whether they're equal or not. The factored form are the ones that we have our new critical value, which is the whole. So there's a whole, so now I have to factor everything. Normally it's just going to be a quadratic. I'm not going to make you factor this thing. But you should be able to factor a quadratic either using GCF, basic, AC, or difference of squares. If there's a factor that's exactly the same on the top and the bottom, that's called a common factor. If there's a common factor, then there's a hole in the graph. So looking at the top here, we have which factors on the top and the bottom. We have the x minus 1 here, and the x plus 5. So this factor and this factor are exactly the same. So that means we're going to have a hole at those values. So these are going to be actual coordinates. So right here, x minus 1 means there's a hole at positive 1. The thing is, it's not 0. We have to actually find what y is, but we'll do that by plugging in when we get to our actual examples. Right now, let me see. I'll just leave it as y. And then the other one, since there's a +5 here, there's a hole at -5. But then we'd actually have to find this y value. So I'm going to call this y1 and y2. We have to do it by plugging in, but we're not going to plug it into this thing. Okay, so that's the common one. Once you find the common one, you throw out those factors and you see what's left. So if you look back over here at our simple rational, the numerator gave us the vertical, or sorry, the x-intercepts. That's still going to be the case here. So here, let me get a different color. So if we look at the numerator, the stuff that's left in the numerator is still going to give us the x-intercepts. So the x-intercepts occur when y is 0. In order for a fraction to be 0, you set the remaining factors of the numerator and solve for x. So like right here, here's a factor. That means this x-intercept is at +3, 0. Here's a factor. That means the other x-intercept is at -3, 0. So the thing is, it's what's left. You have to cancel out the whole first, and then whatever's left is the x-intercept. And then likewise, whatever's left in the bottom, because the bottom gives us our vertical asymptote. So whatever's left in the denominator gives us the vertical asymptotes. So the vertical asymptote is when the fraction is undefined. A fraction is undefined when the denominator is 0. So you set the remaining factors of the denominator equal to 0 and solve for x. So here are the remaining factors of the denominator. So those are going to be x equals +2 for this one and -2 for that one. So I'm just going to write it as plus and minus 2. Okay, so that's the main idea of this section. The rest of it is just actually doing problems over it. So that's what we're going to be doing for the rest of these examples. Alright, so this first example here, all it wants us to do is identify the critical values, which are the intercepts, the asymptotes, and the holes. So first, if we look at this form, this is standard form because there's no parentheses, it's all multiplied out. The two critical values that we can get from standard form are the horizontal asymptote and the y-intercept. So these are the two we get from standard form. So in standard form, the y-intercept are the ratios of the constants. So the constants are these two numbers. So y equals 12 over 8. But we do reduce that. They can both be reduced by 4. So here we're going to get 3 over 2. But you always write this one as a coordinate. So 0, 3 over 2. Right? And then the horizontal asymptotes, the first thing you have to look at, before you look at the coefficients, you have to look at the degrees. So the degree of the numerator is 2, and the degree of the denominator is 2. So they're both squareds. So this is N and this is D. So since the numerator degree equals the denominator degree, then we can look at the coefficients. But you don't do that if they're not equal. If they're not equal, well then it's either 0 or none, depending on which one is bigger. Okay, so here the coefficients are 1 and 1. So 1 over 1 reduces to just 1. So the horizontal asymptote's at 1. So now for the other ones, we have to factor the numerator and the denominator. So here, oops, very crooked line. For the numerator, we have 12. So factors of 12 that add to 7. So they both got to be positives. And 12 is going to be 3 and 4. So +3, +4. And we do the same thing for the denominator. Factors of 8 that add to 6. So factors of 8 are 2 and 4. To make positive 8, they both got to be positives. Alright, so here's our factored form. So now to find the whole, we figure out what is common between the numerator and denominator. So this x plus 4 is common. So then that means the whole is at negative 4. Now it does have a y. I'll show you how to get the y in just a second. But right now we're just going to leave it at negative 4 until we find the other values. So now we cancel them out. And then we see what's left. So the vertical asymptotes are what remains in the denominator. So the factor of the denominator is x plus 2. So that means the vertical is at negative 2. And then over here, the x-intercept is what remains in the numerator. So the factor in the numerator is x plus 3. So that means there's a x-intercept at negative 3, 0. You set the numerator equal to 0 and you solve. Okay, so from here, the way we find the y-coordinate of the whole is you take this reduced form and into the x you substitute in the negative 4. So we have x plus 3 in the numerator and plus 2 on denominator. Then we just take, instead of x and x here for the x's, we replace it with the negative 4. So negative 4 and negative 4. And this is how you find your y for the whole. So negative 4 plus 3 is negative 1. Negative 4 plus 2 is negative 2. So this tells me that the y is going to be at positive 1/2. So the point, the actual open circle in the middle of your graph, is at negative 4, 1/2. So the whole is a coordinate. I'm not always going to ask you in coordinate form. Sometimes I might just ask you what is the x value. But if you're trying to graph it, you do need the y in order to figure out where exactly you're going to put your open circle. Okay, so this is what we're going to be doing for most of the next pages. Some of them we actually graph them, but the important part is that you know how to find them. So on the next page here, again, we're still just finding these critical values, and then we finally get to graphing it on this example. So a lot of the rest of the notes is just identifying these critical values in each of the forms. Okay, so now the next example, again, same type of things. We're going to find the critical values, the intercepts and the asymptotes, by writing it in factor form, and then getting the values. So what I always do here is I always see what form it's in and what I can get from that form, and then I go to the other form and see what I can get from that form. So here, this one is standard form. So in standard form, again, we can get the y-intercept and the horizontal asymptote. So the y-intercept are the ratio of your constants. So here the constant is negative 3 and negative 6. So y equals negative 3 over negative 6, and that reduces to 1/2. So this is the y, 1/2, but you always write it as a coordinate, so 0, 1/2. Right, and then the horizontal asymptote. First, you got to look at the degrees. So n and d, these are the degrees. So degrees. So the degree of the numerator is 2. So 2, and the degree of the denominator is 2. So since these degrees are equal, then you can look at the coefficients. And we'll get to examples in just a second when they're not equal. So the coefficients of both are 1 and 1. So 1 divided by 1 is just 1. So that one you just leave as y equals. Okay, these other three, we need to come over here and factor it. So we're going to use basic for both of them, numerator and denominator. So here, negative 3 to get negative 2. So 3 only has one pair, 1 and 3. To make it a negative 2, I need the bigger one to be negative. So negative 3 and positive 1. Alright, the 6 you have to be careful with, Because it's negative, I need one positive, one negative. And I need it to be -5. So the -6 is tricky because I have 1 and 6 that I can subtract, and I have 2 and 3 which I can add. Since I need it to be a negative, I need the 1 and the 6. So I want the bigger one to be the negative. So 6 is negative, and the 1 is positive. Alright, so you always look at common factors first. Before you can do intercepts and asymptotes, you have to see if there's any holes. So is there anything in common between the numerator and denominator? Yes, there is. There's these two numbers. So that means the x-coordinate of the whole is at -1. To get the y, we cancel it out, and we plug -1 into what's left over for the x's. So we're going to plug a -1 here, -3 in the numerator, and then a -1 here, and a -6 in the denominator. So then we just subtract and reduce. So -1 minus 3 is -4. -1 minus 6 is -7. So negative and a negative makes this positive 4/7. Okay, so you get the y-coordinate of the whole by plugging in the x to whatever's left over when you cancel it out. Okay, and then once you cancel it out, you see what remains. So vertical asymptotes are what remains in the denominator, so equal to 0 here. So that's going to be a +6. And then x-intercept is what left in the numerator when you set it equal to 0. So add 3 to both sides and we get +3. And then 0 is the y. So again, if you actually want to do that, equal to 0, add 3, x is 3. That's what we're doing here. Same thing for the vertical. Add 6, add 6, x is 6. And the whole, same thing. But these are just opposites because they're just x equals, or x plus or minus a number equals something. So we don't have to worry about dividing. If there's a number in front of the x, then we have to divide. But not for these examples. Okay. So again, more of the same type of thing. So again, standard form I give you. So from standard form, you can get the y-intercept, which are the constants. So looking at the constants, we have -1 and -3. -1 over -3 is just +1/3. So write it as 0, 1/3. And then you look at your exponents first. So the degrees of the numerator is 2 and the denominator is 2. So since 2 and 2 are equal, then you can look at the coefficients, which in this case, again, is 1 and 1. So 1 divided by 1 is just 1. Alright, so now for the other three, we have to come over here to factored form. So the numerator here is a difference of squares. So how does difference of squares factor? Factors into plus, minus, and then you just take the square root of each. So square root of x squared is x and x. Square root of 1 is 1 and 1. So you factor by difference of squares. Denominator is just another basic one. So -3 to get 2. Well, -3 is only 1 and 3. To get a positive, I need the bigger one to be positive, and then this is negative. Okay, so in factored form, again, you always want to identify the wholes first for the common factors. So the x minus 1s are common. So that means I have a whole at +1, but I need to find the y's. So I'm going to plug a 1 into what's left over. So I have a 1 and a 1. So I'm going to do 1 plus 1 in the numerator over 1 plus 3 in the denominator. So 1 plus 1 is 2. 1 plus 3 is 4. So this reduces to 1/2. So to find the y-coordinate, if you need to, and you're not always going to have to, you plug in the whole to whatever is left over after you cancel it out, after you cancel out the common factor. So now this goes away and this goes away. And the remaining factors, the verticals are the remaining factors in the denominator. So x plus 3 equal to 0 means that x is -3. And then the numerator equal to 0 is the x-intercept. So x plus 1 equals 0. Subtract 1, we get -1. And for x-intercept, y is always 0. Alright. And then we have pretty much the same thing here, but now we're adding graphing. Now we're going to actually use this to kind of sketch a graph. We're not going to be able to graph it perfectly, or completely, but we'll be able to kind of sketch it out. Okay, so for this one, again, we're adding the graph to it. Without a calculator, you should be able to identify the critical values, but then you're going to need a calculator to see what happened, or a graphing app to see what happens in between. So here, again, in standard form, we can get the y-intercept. So let's come down here and get the y-intercept, which are the constants. So that's going to be 12 over 2. 12 over 2 is just 6. That means I have a point over here on the graph at 0, 6. So go ahead and plot your 0, 6 point as your y-intercept. Okay, I can also get my horizontal asymptote. So I look at the degrees first. So degrees first. So they're both squared, so 2 and 2. So since 2 equals 2, then I can look at the coefficients. So the coefficient of the numerator is 1, and the denominator, or sorry, 2, and the denominator is 1. So 2 divided by 1 is 2. So that means I have a horizontal line at 2. And the thing about the horizontal is sometimes it can cross the horizontal, the graph, because the horizontal is just what happens at the ends. So at the ends, it gets closer to the horizontal. What happens in the middle, okay, it might cross it, but that part we really don't care about. We care about the end behavior. Alright, so for factored form, if you look at the numerator, the first thing we see is that the numerator has a GCF, which means everything can be divided by 2. So if we divide everything by 2, we are left with x squared plus 5x plus 6. So now for this one, we can just use basic to completely factor it. You could have used AC, but then that takes too long. So if there's a GCF, you use GCF, and it won't take you as much time. So here, factors of 6 that add to 5. So now this time they're both going to be positives. So here I do want to use the 2 and the 3. Now the denominator. So 2 to get 3. So 2 is only 1 and 2. 1 times 2. To get a positive 3, they both got to be positives. Okay, so now let's check. Are there any common factors? Well, we have a plus 2 here and a plus 2 here. So that means the x-coordinate of the whole is -2. And this is really where you need the actual coordinate, because where at -2, it's not an intercept at -2. No, it can be anywhere at -2. So to figure out exactly where, I got to plug in. So here, let me cancel this out and cancel this out. So I'm going to plug a -2 for the x in the numerator. So we have 2 times -2 plus 3. And plug it in the denominator, -2 plus 1. -2 plus 1. So here, negative 2 plus 3, that's just 1. 1 times 2 is 2 in the numerator. And in the denominator, negative 2 plus 1 is negative 1. So 2 divided by negative 1 is just negative 2. So that means the y-coordinate is negative 2. So at this point, negative 2, I'm going to have an open circle in the graph. I'm exaggerating it. The thing about this one is if you graph it in the calculator, you're not actually going to see an open circle because it's so small. But you have to know that it's there. You'll see it in the table, but you won't see it in the graph. So I'm kind of exaggerating the whole. Alright, so now you get the rest of the points. So verticals are what's left in the denominator. You set it equal to 0. So here equals 0 is just going to be a minus 1. So draw your graph line at negative 1, your dashed line. And then the x-intercepts is what's left in the numerator when you set it equal to 0. So here, I mean the 2 really is not going to make a difference. You can distribute it back, but then you're going to end up dividing it anyway. This is the only part that matters. Equal to 0, the factors, because this 2, that's never going to be 0. That's not going to affect anything. Here, the x-intercept is at negative 3, 0. So negative 3, 0 is a point. Okay, so this one actually does end up looking like a hyperbola, but not all of them are. So to check for sure, we're going to go to a graphing application called Desmos, since we don't have graphing calculators yet, or you might not be able to. So in Desmos, you'll be able to graph these functions. So here's the one we're trying to graph. So it just gives you the sketch, it doesn't give you the asymptotes. That's why we have to graph it. It gives you the x-intercept here, the y-intercept there, the whole, like you can't see it, but it's undefined. So if you go right here, it says undefined, but you're not going to see it when you just graph it normally. Okay, but this, the only thing you need this for is to figure out how to connect your dots, how to connect the rest of your graph. So the actual graph is this piece over here. Goes through that point, but jumps over this hole. Doesn't cross the vertical. Here, goes through this point, and approaches the horizontal. Okay, but not all of them are going to look like this hyperbola. Okay, some of them look, I mean, they all look different. They have 3 asymptotes or 2 asymptotes, and then it looks weird. They're going to look weird. Okay, so the next part, more examples like this, but now we're not going to have the same degrees. And then we'll see what happens when we have a slant asymptote. That's going to be the next part.